Hello again. Welcome to Space Nuts, where we talk astronomy and space science, and occasionally we'll answer questions. We get a lot of questions and we talk about them, but answering them, that's tricky. But we will attempt today to answer questions about background modulation, also turning energy into matter, which follows up from something we spoke about not too long ago, spin rates in space. What are they? Why do they happen? Why can't we just have, stuff standing still and not taking any notice of us? And a question about moving spacecraft in space, or more specifically, not moving them. What happens there? That's all coming up on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Fred Watson, even Fred Watson, is with us again to try and answer all of those. I almost forgot your name, Fred, and it's only been, mere seconds since we last spoke in real terms.
Yes, it's extraordinary. We're wearing the same clothes as well. It's quite remarkable.
Yeah.
What a coincidence.
I've had these on for 4 straight days. So
really?
What could be the problem? Oh, hello, you've got a visitor.
I do, because Marnie's got to go out. She's just giving you a wave.
Okay.
She's just delivering Geordie so that Geordie doesn't leap around.
Ah, okay. There he is.
See you later.
Bye.
Yeah.
You've got people at the window, people at the door, dogs in the lap.
There you are. There's Geordie.
Hello, Geordie.
Hey, hello.
Oh, yeah, that got some
He
attention.
does not know what is going on. He's saying, what, hang on, what's happening here? Now my headphones are caught up in his paws, so...
It's almost like live radio. Well, you never know what's going to happen. What do they say? Never work with children and animals?
Children and animals, that's right, yes.
It's often true.
It is.
Shall we get our first question?
Yes, we better, before the dog starts barking.
Oh, I don't mind. I like it when he joins in. This question, Fred, comes from Craig.
Professors, it's Craig from sunny Maroombula in New South Wales once more. This question is from the Spanner and the Works department. You've just been talking about the background gravitational modulation of the space-time continuum picked up by the pulsar timing arrays around the world. Could these modulations have an effect upon the cosmic microwave background? Could they be the reason why there is a minute difference between the high and low microwave amplitudes? Just thinking about it. If you've got a good answer, I'd love to hear it.
You're very hopeful, Craig. Good answer. I mean,
Yeah,
gee
that's
whiz.
fine.
Put the pressure on.
What do you think this is, a
Yeah.
podcast or something?
Gosh. Gee whiz. Background modulation. Do you want to expand on what he's referring to before you answer the question?
Yes, and you put it...
Good, because I had no idea.
No, you put it in a nutshell beautifully when we talked about it. So we're talking about gravitational waves, which are ripples in space-time itself. But you drew the analogy of ripples on a pond.
Ah, that's right. I did too.
And that's right. So ripples on a
All
pond.
running into each other.
Hang on a minute. What?
Sorry, it's Hanson these you.
Oh, okay. Have you got time to do it?
Yes, just.
All right. Yeah.
Just take the handbrake off and let it go.
Yeah, well, it would. We live on the side of a hill, and it wouldn't stop till it got to the bottom of the valley. Demolish a few houses. So, I wonder what's going to happen next.
I don't know. It's been
Why
fun.
does the painter need me to move my car? I don't know. Probably wants to. I think he probably wants to touch up a wall that he's parked next to it.
Possibly.
Oh dear. Anyway, yeah. So your lovely analog. You've got a pond, water, and what we've detected mostly in gravitational waves is things colliding, like black holes, basically spinning to amalgamate together, or black hole and a neutron star, or two neutron stars. Those all create gravitational waves. And you drew the lovely analog that's like throwing a rock in the pond, because then you get these ripples spreading outwards. and that's what we measure. That's what we detect with the gravitational wave observatories. But then you said, okay, don't throw a rock in, pick up a handful of rocks and throw them in. And what you've got now is a sort of background set of ripples coming from all different directions, all different intensities. And that's what we mean by the gravitational wave background, the analog of that in space-time.
Okay.
So Craig's question was related to whether that could influence our view of the cosmic microwave background radiation, which is the microwave signal from the Big Bang. It's us looking back in time so far, because of the finite travel time of radiation, us looking back in time so far that we see back to a time when the universe was glowing brightly. It was opaque, it was glowing. And the bottom line with that is that because the universe is expanded by something like 1,300 times since that the universe became transparent, since the fog cleared, if I can put it that way, that's why we see this in microwaves rather than in visible light. But what we also see is these tiny variations in the intensity of those microwaves, which is what Craig is alluding to. Now, those are very well understood and are caused by slightly different temperatures in the fireball of the Big Bang, which are caused by sound waves moving through it. It's the bang of the Big Bang. It's what we call baryonic acoustic oscillations, which means sound waves. And so they are imprinted on the cosmic microwave background radiation. What Craig has put his finger on is the bit that we don't understand, which is why the picture of the universe that we get, the picture of the expansion of the universe that we get from that is different slightly from the expansion of the universe that we measure today by today's galaxies moving apart. I think it's a great postulate to put forward, Craig, but I don't think the gravitational wave background radiation will actually influence that at all.
Okay. Very good. Thank you, Craig. We're getting a few live questions through on YouTube, and if we've got time at the end, I'll jump on those, but timing's a factor at the moment. Text question from John. Actually, he's got two questions. He said, "Hi, guys. You're still the best despite the competition." You're talking about podcasts or soccer? I'm not sure. Just a question or two for your potty, if you choose to use them. Einstein told us that matter is concentrated energy. Has it ever been attempted to turn energy into matter in the lab? I suspect not, but how would you go about it? We'll just deal with that one first, and we'll just jump to his second question next.
Let's do that, because the answer is yes. An experiment done some years ago at an atom smasher called the Relativistic Heavy Ion Collider, U.S. Department of Energy Office of Science User Facility for Nuclear Physics Research at the Brookhaven National Laboratory. That actually has produced, this is a report from 2021, so this is only 3 years ago. It's basically, they've basically demonstrated that you can combine photons and you get matter.
Wow.
You also get antimatter. And so the two probably annihilate and immediately create another photon. But the accelerator did do exactly what John is asking about. You take energy and you turn it into matter. Now, it doesn't last very long, but the phenomenon is there. So it's usually the other way around that we're thinking of. The nuclear reactions in the sun are turning matter into energy all the time. Atomic energy is doing the same thing. Nuclear weapons are doing the same thing, but we tend not to think in terms of putting energy into the form of matter. But it has happened at the Brookhaven National Laboratory, and you can find basically a report on that on the Brookhaven National Laboratory newsroom webpage.
Would I be stretching a long bow to say, look, it happens naturally on Earth? It's called photosynthesis.
That's a really interesting question, because photosynthesis does involve quantum processes, but I don't think it's a turning of matter into energy. I think what it is.
No, I meant the other way around, energy into matter.
I beg your pardon, energy into matter. Yes, sorry. I think it's sorry, quite right. I think it's more like the energy facilitating chemical reactions.
Okay.
Rather than atoms being produced. So it's that, you're not finding protons popping out or anything like that. It's more about the chemistry rather than the nuclear physics of it. So that's the idea, but I think the answer is no.
Okay. John's second question is totally unrelated. What makes the Earth spin at such a constant speed? In fact, why does it spin at all? Do all bodies in the known universe spin at constant rates? What establishes the spin rate? John Noon.
So, yeah, great questions. To all intents and purposes, it is a constant speed. It does vary very slightly. But the reason why it spins at a constant speed is that it's just a big flywheel, which is spinning because there's nothing really to stop it. It is losing spin energy, and that is going into pushing the moon further out in its orbit. But that's at a very low rate. What is it? The day increases by 3 milliseconds per day per century, I think, is the bottom line there. So it's very, very small. But it's a question about why does it spin at all? And do all bodies in the known universe spin at constant rates? Everything spins, and that's because of the way things are formed. Usually, when let's take the case of a star. You start off with a cloud of gas, and dust probably mixed in with it. That it's in motion. It's got little eddies within it. Little bits of it are spinning at different rates, but it's collapsing under its own gravity. And eventually, during that collapse, a particular kind of spin becomes the dominant one, until the whole thing winds up spinning. And the more it collapses by the conservation of angular momentum, the faster it spins. And so that's why we've got a sun that spins once every 27 days or so, and a set of planets going around it, because they're formed from a spinning disk as well. And most solid objects and even galaxies in the universe formed by this collapse mechanism. So they're all spinning. And now, his second bit, do they spin at constant rates? Not necessarily. We know some neutron stars are very, very, they're spinning, they're very, very accurate clocks. Their spin is very, very constant, but there is an energy loss caused by gravitational energy actually taking the spin down slightly. So there is a reduction there. So, yeah, it's the physics of their formation that establishes the rate of spin, to answer your last question. It's a great set of questions, John, and thank you for asking them.
Very good. Thanks, John. And, I'm glad we could actually nail that one pretty concisely. This is Space Nuts, Andrew Dunkley with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, Fred, we've got another audio question. This one comes from Nigel.
Hello, fellow space nuts around the world. Hello, Fred and Andrew. This is Nigel from Brisbane, Australia. I have a question that is science fiction versus science fact. I've been watching a TV show called The Ark. It's been around about a year now. In it, there's a scene where two spaceships decide to meet up in interstellar space.
Jeez.
And in the shot, it shows the two spaceships meeting up, and they're perfectly still. And that's my first question of two. In interstellar space, if two spaceships met up, would they be perfectly still, or would there be something causing them to drift and move apart? And that's my second question. Is there any energy forces out in interstellar space, such as solar winds, etc.? Okay, love the show. Thanks for taking my question. See you soon. Bye.
Thanks, Nigel. I suppose that's reasonably simple to answer, because we send spacecraft up all the time to dock with the International Space Station, which requires manoeuvring thrusters, retro rockets, whatever you want to call them. But I'm assuming that he means if they were to meet in space face to face, no engines or anything, now it came to a dead stop, would they stay where they are? I think that's what he's getting at.
Yeah. Probably not really. This is called station keeping. It's when you've got spacecraft that you want to remain in a particular position within its orbit, of course, because everything's moving at least 8 kilometers per second, or at most 8 kilometers per second in low Earth orbit. And there will be mechanisms that cause a drift. So the questions that Nigel's asking are the ones that really spawned the Gemini missions in the 1960s, the space missions where the two-person spacecraft called Gemini or Gemini, depending on how you pronounce it, tried out the ideas of rendezvous and docking. Because until then, nobody really knew how stable these things were going to be when they were in orbit. The physics says that they should be very stable, but there might be a slight drift because of gravitational perturbations, for example. And also, as Nigel mentioned, the solar wind is a factor in working out whether a spacecraft is going to stay put or not. So there would be slight drifts, and that means that you're always going to have to tweak it with your thrusters. And that's why the thrusters are so important on rockets. It's actually why it's not the Dreamliner, is it? It's the
Boeing Starliner.
Starliner, that's the one, yeah. The Starliner. I know it's a Boeing product. That's why the Starliner's stuck up there at the moment, because its thrusters are not behaving properly, or there's doubt that the thrusters might work properly. And that is vital if you're maneuvering a spacecraft next to another one, especially a big thing like the International Space Station. So, yes, the answer is it's a tricky business. You can't just park too close together and expect they'll stay put.
Well, they've always portrayed that well in Star Trek. When they lose all power, they start floating away somewhere. So, but that would be momentum, I would imagine. But yes, thanks, Nigel, for the question. Have you got time for a couple of quick questions without notice, Fred?
Just a couple of quickies? Yeah, I've got
all right.
Yeah.
This one comes from, these are YouTube questions that have been sent to us live today. Sloth Dad has sent us a question. I'd love to know how you got that name. Hi, guys. What are your views on using helium-3 from the moon's regolith as fuel, providing we create the technology needed to extract, transport, and fuse it? Should we be using the moon's resources or using the moon for its resources? I know you've got strong opinions on this.
It's a really great ethical question, actually.
Yes.
And I mean, we're going to face it very soon, because the most abundant resource that we can lay our hands on with present technology is the water in the southern polar region of the moon. We've got evidence that there's lots of water ice there. Who does it belong to? Well, the Article 1 of the International Space Treaty of 1967 says nobody can own anything in space. So it's
but they can own what they take, can't they?
If you grab it, you can.
Where's the line there?
Yeah, that's right. So I don't. I think it's inevitable that we're going to use that water for breathing and oxygen and rocket fuel and the rest of it. Helium-3 is a step further, and it becomes an even more ethical conundrum, because it's potentially a resource that could benefit humankind generally, not just few space explorers, because helium-3, we don't even know whether it's practical or not, but has a certain promise of very cheap and safe nuclear energy by nuclear fusion. That's a long, long way down the track. The ethics of whether you mine it and bring it back, and you've got to bring back a lot of lunar regolith, the lunar soil, in order to get the helium-3 out of it. The ethics of whether that is worthwhile economically or from an ethical point of view, are questions that I think will need to be addressed before we start mining it. So you've raised great question, Sloth Dad, and I like the name too. But at the moment, the jury's out a little bit. I think it's inevitable we will wind up using the water, though. And, whether it's ethical or not, that's what's going to happen.
It will happen. Ethics doesn't seem to get in the way of things sometimes. Thank you, Sloth Dad. And one more quick one from Grant. I say space does not warp or bend, with only the matter, energies, frequencies and forces, some not fully understood and others yet to be discovered, give the illusion of space warping or bending. LOL. Can't prove it wrong, though. So he's made a statement. I say space does not warp or bend.
Yeah, you can demonstrate that space does warp or bend when it's empty, because that's how gravitational waves are propagated. It's an object that's responding to that when we pick them up with a gravitational wave detector. But the space they're traveling through is devoid of stuff. And it's space itself that bends, as was predicted by general relativity. And Einstein was very seldom wrong.
Well, yeah, and even though his famous predictions or theories he believes are wrong, or one of them specifically, and yet no one's been able to prove it wrong. General relativity. They're still working to break that one, aren't they?
Just to see whether any holes in it, because holes, things that don't work in general relativity, which is so perfect, might lead us to new physics. That's why people are trying to break it.
Fascinating. Thank you, Grant. Lovely to get your question without notice. Nice to get those from time to time. That brings us to an end. Don't forget to visit our website if you get a chance, spacenutspodcast.com, spacenuts.io are the two URLs you can use and have a look around while you're there. You can send us your questions via the website on the AMA tab, or the Send Us Your Questions tab on the right-hand side of the homepage. Don't forget our sister podcast, Astronomy Daily. You can listen to episodes there as well. And if you're a YouTube follower, don't forget to click on subscribe, and a reminder too, if you want to join like-minded Space Nuts listeners, you can do that on the Space Nuts podcast group on Facebook, because it's a great little community and growing all the time. I think they've got a few thousand followers now. It's quite extraordinary. Anyway, any way you can get in touch with us, we're happy to try and help you out with your questions every week on Space Nuts Q&A. Thanks, Fred. As always, it's been great fun.
It has. It's been a good session today, and hopefully we'll have another one next week. So let's call it a day, and I'll see you then.
Okay, thanks, Fred. See you soon. Fred Watson, astronomer at large, and thanks to Hugh in the studio for helping out today, getting those questions through to us, and helping Fred with the painting later, apparently. Oh, no? Oh, well, he is now. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.